Okay. So if you're watching this video, they've already done this activity. For everybody in here, though, somebody tell me what you put in the first block. 2.5. How did you get 2.5?
You multiplied the velocity by the time.
And why, if the velocity is changing from 0 to 5, why did you pick 5 and not 0 or some number in between? There's no wrong or right answer here. I want to create a discussion. So it has to be between 0 and 5. So picking 5 would be a totally legitimate answer. Okay, now, using that same method, in the next half-second interval, okay, right here, which of these two numbers should I pick if I'm going to be consistent with my method? 7. And remember, the time is always 0.5. So we're saying distance equals velocity times time, and time is always 0.5 or 1/2. So I should do 7 times 0.5, and I should get 3.5.
So were we supposed to be consistent?
You didn't have to be consistent. I'm just kind of creating the discussion. So for anybody else, out of these two numbers now, which number should I pick?
8.
The 8. 8 times 0.5 would be 4. Now that was one way to have done this problem, and we could continue it on. I'm not really that concerned with that. Okay, now did anybody from 0 to 5 pick not 5, but something else? Did anybody pick 0 or 2.5? Why would you pick 2.5 here?
It's in between 0 and 5.
It's in between, and then you'd multiply by 0.5. And so here, you would have 1.25. That would be an okay approximation here. Using that same method from 5 to 7, the velocity was 5, then it was 7. What one number could you say, overall, this is the velocity? 6. 6 is between 5 and 7, so you multiply that by 0.5 and you get 3. And notice my answers are a little bit less. Okay, because before I was picking the bigger number each time. So that's what we call an over approximation. This is a little bit better. If we had picked the smaller number each time, it would have been an under approximation. So I'm not so concerned with what you have here, but you should have, in the end, had something between 45.5 and 55 feet. It should have been something between here, and probably the most methodical people came up with 50.25 feet. I'm not saying that's the right answer, but that probably is the best approximation. Now, we are not really using calculus here, but I'm using this activity to introduce a calculus concept that we're going to call Riemann sums. This is pretty vague, huh? We don't like vague, right? We like black and white, we like concrete. So we're going to get to that part of it here in just a minute. I'm going to give you rules, and you're not going to just, it's not going to be like, just pick a number. I'm going to tell you what to do in the next problems. Do you see how sometimes you could tell if it was an over or under approximation? Like when I was picking the bigger number, that was kind of like obviously over. If I always pick the smaller number, maybe that's obviously under. But this number, I don't know if it's over or under. It's probably not exact, and in fact, I don't have any way to know if it's exact. Okay, I have one more question to ask, and that is, if we were wanting to get a more accurate answer, okay, we've already talked about how we can manipulate the numbers and that doing numbers in between give us a better answer. But what could I have done in the experiment to have made my answer better? So let me read this out loud, and I'm going to emphasize some words so it'll be really easy to pick up on this. A gorilla jumped off the top of a building. We were able to record the velocity of the gorilla with respect to time twice each second. The data is shown below. How could I recreate this experiment and get a more accurate answer as to the total distance?
Every 1 second.
So
measure it more times per second.
More times per second. And if I could measure it basically constantly, if I had some kind of machine or motion detector or something, then that would be an even more accurate answer. And that gets into calculus right there. Okay, so we're not doing that yet. We're still just today and all week going to focus on just approximation. Okay, so this whole concept of multiplying a rate times a time to get the distance, that's what we're going to do now. All right. So I want you to turn to page 2 on your packet. All right, now, we just did an activity that was kind of vague and you had to make some choices. Okay, I want you to just for a second, before we even get into this, I want you to look at the words that are underlined in A, B, and C. I start giving you very specific words, okay? That's going to tell you which number to choose. Okay, so let's look at the similarity between this and the gorilla problem. A car is traveling so that its speed is never decreasing. Okay, we can see that. The speed is increasing. We're given a table, we can see it. We're given a graph, we can see it. During a 12-second interval. The speed at various moments in time is listed in the table below, and the graph is also provided. Now, in the future, you're only going to be given a table. So, the graph is nice. It's going to help us learn how to do this and kind of make connections. But eventually, you either need to be able to do it without the graph or you need to be able to draw the graph on your own. Okay? But for now, we'll use both of them. So this part A says using 3 subintervals of equal length. Okay, so a subinterval, you know, the interval is 0 to 12. A subinterval is going to be like 0 to 2, 0 to 4, 0 to 6, something like that. If they're of equal length, how long is just one subinterval? So the total is 12, and there's 3 of them. 4. So each subinterval is 4. Okay? So that's important. Estimate the distance traveled. So this is just like what we did a second ago. So I know I'm going to be multiplying some numbers. During the 12 seconds by finding the areas of the 3 rectangles drawn at the heights of the left endpoints. This is called a left Riemann sum. That's just the name of it, this method. So I'm going to show you first on the graph. Okay, so if my subinterval is a distance of 4, okay, my rectangle is going to have a base of 4, and the height is going to be determined by one of these points. Since they said use the left one, I am going to use the left one, and I'm going to draw this rectangle. Okay, the area of that rectangle is what tells me what the distance traveled is. Okay, so we need to know the 2 dimensions. The base is 4, which I already knew, that's our subinterval. What's the height of this rectangle? 5. Okay. Now let's look at this up at the table because again we're going to have to eventually get used to just doing this only using the table. So 0 to 4 we have 3 different speeds, 5, 12, and 21. For a left Riemann sum I need to use the left number 5 and I need to multiply that by the time, which is 4. So whether you're using the numbers from the table or the graph, you get 5 times 4. It's the area of the rectangle. That represents the total distance traveled. Okay, now that's just one subinterval. Okay, we have 3 to go. So from 4 to 8, that's the next rectangle. Which height am I going to use for this rectangle if I'm doing a left Riemann sum? 21, this point right here. That's going to determine how tall this rectangle should be. And so I'm going to add that. I'm going to go 21 again times 4. Subintervals don't have to be equal length, but a lot of the time they are, and in this problem it told us that they are. We'll work our way up to when they're not. So 21 times 4. Now if we looked up here on the table, this is maybe how you would want to organize this. Notice that there's a little bit of an overlap. That's because the first subinterval was from 0 to 4. The second one is from 4 to 8. So 4 ends and starts from one to the other, okay? So then we use 21. All right, and then we add. Now what would the third rectangle be? 45 would be the height. 45 times what? 45 times 4. Again, it's times 4 because all the subintervals are 4. Just like in the gorilla problem, all the subintervals were 0.5. Now, when you're typing this in, you may want to do something like this, just to create a little bit less typing in the calculator. It's not that you have to simplify here, but we're going to want to compare our answers. So let's just go ahead and multiply this out using either your calculator or your phone. Okay, I got 284. If you're not getting 284, just double check your multiplying and adding. The next thing is we have to figure out what the units should be. There's two ways to do this. One is just logically estimate the distance traveled. So what would that be? If we're doing distance, feet. Okay, here's another way to do it, which is going to be more helpful in problems that are not velocity oriented, because really we can do this, and we're going to open this up to lots of different types of problems. Think about what we multiplied. We multiplied 5 feet per second. I'm going to write that as feet over seconds, and I multiplied that by 4 seconds. Right? Here are my units. Each time I did feet per second times seconds, feet per second times seconds. And look at what happens to the seconds. They cancel out and you're left with just feet. So you can determine the units multiple ways. It's a good check. Now, thinking back to the question from the gorilla problem, do you think this is a good answer that represents the true distance this car traveled? Like in the first 4-second interval, is this accurate to say that the car traveled 5 feet per second the whole 4 seconds? Look at the velocity. It increased, right? So would you say this is an over or an under approximation? Under. Okay, under because the speed was increasing. All right, and we're going to focus more on that whole over and under stuff tomorrow. But I just wanted to kind of get it in a little bit today. All right, now if you look at B, all the words are the same except for one word. One word change. What is that? The right endpoints. This is called a right Riemann sum. So you do have to know the difference between your right and your left. My mother, God bless her, she struggles with this. Some people do. So you got to figure out a way to make sure you can keep your right and your left. I know that seems silly, but some people just get it mixed up. You got to make sure you can do that. All right, now, notice, let me continue this from the last problem. So notice there, the 3 subintervals, they're always overlapping. You don't have to redo everything, by the way, okay? But out of these 3 points, you are picking the right point. So I'm going to do this one in blue, and you can tell that it's going to be bigger. All right, and I'm picking the 21. All right, how does this new first rectangle compared to the old second rectangle? It's the same, right? It's kind of like they're sliding over, and that you're going to notice that happening a lot. So my first rectangle is going to be 21 times 4. Okay, now what about the second rectangle? Now if I'm choosing the right, okay, or if you're looking at from 4 to 8 here, and if you need to, just kind of like put your hands on there and say, which of these 3 speeds am I going to choose? Choose the right number, 45. 45 times 4. And then what would the third one be? 65. And again, when you type this in your calculator, you're probably going to want to do something like this, but that's up to you. And you should get 524, and the units are still going to be feet. Okay. So this is a lot bigger. Do you think 524 is a better answer than 284? I don't know. It's an over approximation. Probably the best answer is somewhere in between here. All right, let's look at C. So C brings up a third type of Riemann sum, and that is called a midpoint Riemann sum. This is not a different problem. This is the exact same table and graph. It's just there so you don't have to draw over the same graph a million times. So again, you look at your from 0 to 4. Now instead of choosing 5, which was the left, or 21, which is the right, you're going to choose 12 to represent the speed over that 4-second interval. So 12 times 4. On the graph, still the rectangle would be a base of 4, but the height would be determined by the middle point. So it's the same kind of thing. I'm just choosing the middle number, not the left or the right. Go ahead and see if you can finish this one out on your own. Okay, what are you guys getting here? 392 feet. So far out of these three answers, which do you think is the closest to the true answer? Probably the midpoint. Is it exactly right? Probably not. It's probably a little over, a little under. We don't really have enough information to decide that yet. Okay? All right, now let's, for me, I'm going to go to the next page. You've got to flip all the way back to page 3 since it got out of order. So it's towards the beginning of your packet. All right, so here we have a fourth one called a trapezoidal sum. So we're not using rectangles anymore, we're using a trapezoid. Now, do you guys remember what a trapezoid is? Hopefully you do. Okay, this is probably how you feel like most trapezoids look like. Okay, they don't have to look exactly like that, but they have two parallel sides and the other two sides are not parallel. You have two bases. You have like a base 1 and a base 2, and then you have a height. In the area, you might have memorized a formula, but here's what I'm going to suggest you do. Average the two bases, base 1 plus base 2 over 2. So average base 1 and base 2 times the height. So it's just like a rectangle, base times height, except you're averaging two numbers. Okay, so this is what it looks like on the actual graph. Still 3 subintervals, so I'm still going to be dealing with 4. But look what's going to happen here. I'm going to connect these 2 points. Now, I may or may not go through this point. It may or may not happen. I don't really care. I'm not even really looking at that point when I do trapezoidal. Okay, that's only for midpoint. So I'm trying to figure out what is this area. Now, this trapezoid is on its side from what we're used to looking at it. Okay, do you see the two bases? The two parallel sides are 5 and 21. And the height, because it's on its side, is 4. So however you need to remember this, I like to think of it as a sideways trapezoid. But you're going to have to average those two numbers, 5 and 21. So add them up, divide by 2, and then multiply by your height, which is 4. And we were multiplying by 4 the whole time, so that's not new. So trapezoid is when you don't pick a velocity or speed, you average two of them, the left and the right, basically. Okay, so that would be the first one. The second one, you'd connect those 2 points. And so it's still a height of 4, but this time you'd be averaging, whoops, not 30. You'd be averaging 21 and 45. So go ahead and write the third trapezoid formula down and see if you can multiply and add all that up. And of course here you could try to simplify this or just put it in your calculator. You do have to be careful with parentheses here since you're adding and then dividing 2 numbers by 2. So just pick a method and stick with it. And you should be getting 404 feet here. Okay, your homework tonight, which you have enough time in class actually to do, is to answer these analysis questions here. Okay, this has to do with the problem we just did on pages 2 and 3. All right, we're going to talk about this tomorrow. We're going to talk more about under and over approximation tomorrow, and then we're going to kind of do some more Riemann sums problems. Okay, I've already taught you all the concepts. All we're going to do now is just practice them the next few days. All right.